He is an internationally acclaimed scientist and explorer, leader of 50 expeditions to some of the remotest reaches of the planet, including many field seasons traveling across previously unexplored regions of Antarctica, many first ascents of mountains, and considerable high-altitude experience in the Himalayas and Andes. He has 350 publications and 2 popular books, The Ice Chronicles and Journey into Climate. His contributions to science include discovery of human impacts on the chemistry of the atmosphere, modern Antarctic and Himalayan ice loss, abrupt climate change, and the impact of climate change on past civilizations. He has received numerous honors, including the first ever internationally awarded Medal for Excellence in Antarctic Research, the International Glaciological Society Seligman Crystal, and the Explorers Club Lowell Thomas Medal. He developed several highly prominent international research programs into Antarctica, Greenland, and Asia, and public outreach efforts with organizations such as the American Museum of Natural History and the Boston Museum of Science. And he has appeared hundreds of times in the media, on Nova, NPR, BBC, CBS 60 Minutes, and most recently Showtime's Emmy Award-winning climate change series, Years of Living Dangerously. I present Dr. Majewski.
Thank you, Dan. It's a great pleasure to be here and to be able to speak to this audience. As has been demonstrated many times by the Emirates Center, knowledge leads to opportunity. And of course, many of the presentations that you've heard today have demonstrated that. One of the things that Dr. Rashid said in the very beginning of this conference is that many of the models for future climate have actually underpredicted what climate is. And that's actually the basis for my presentation. It's very important that we not underestimate or underpredict what the capability for climate change is. So I'll take you through a series of PowerPoints that show you, take us back in time and take us forward in time as a tool for learning how not to underpredict. The Climate Change Institute at the University of Maine has a very close partnership with the School of Policy and International Affairs. And our institute is one of the oldest climate research units in North America, arguably in the world. We approach the study of climate in a very, very broad way. We look at the physical, the chemical, the biological, and the social applications, implications of climate change, and we do it in a relatively unique way that's represented by these 3 red bars. If you look at the center one, we, like a lot of climate units, look at the last roughly 100 years of humanly recorded records. Some places this record is significantly shorter than 100 years. We also look at the last 30 years of satellite data, which give us a very, very fine, detailed look at how the climate system has evolved over 30 years. But the thing that we do that's different than many other research units is we take a look at the past, in particular to find out how much the climate system can change and how fast it can change. Because in the last 100 years of recorded records, we don't have the full breadth and understanding of the dynamics of the climate system. So we take this understanding of the past, combine it with what we know from the very detailed satellite and instrumental measurements of the present, and put them together to do not only monitoring to understand what's going to go on in the future, but to do modeling that takes us into the future. We do this in many different ways. The technique that I'm most familiar with is to go to glaciers all over the world, and on the right side you see a series of dots. These are the general locations of the sites throughout the world that we have collected in both polar regions and high altitude regions, records that provide us with extremely robust understanding of how the climate has changed, storm by storm, season by season, going back decades, centuries, and in some cases, many, many millennia. From these records, which are the most robust way of understanding how the climate has changed, we can understand past temperature, precipitation, atmospheric circulation patterns, sea ice extent, biological productivity, volcanic activity, forest fires, changes in solar activity, changes in greenhouse gases, changes in pollutants, trace metals, radioactivity, on and on and on. One of the research programs that I had the great honor to lead about 20 years ago had as its challenge to recover the longest, most continuous, most highly resolved record of the climate system that can be gathered using an ice core from the Northern Hemisphere. It was called the Greenland Ice Sheet Project 2. We spent many years recovering a record that took 10,000 feet of ice drilling to recover, but from it we were able to go back in time year by year, 110,000 years. This is a very important accomplishment because it's the first time ever that we have been able to see in this sort of detail how the climate changed over a very, very long period. Now, prior to doing this research, the view of the way the climate system operated can really be encapsulated by that upper right-hand global temperature. If we were to look at how the temperature changed over the last 120,000 years, we'd find that it gradually cooled to about 20,000 years ago when there was significant more ice cover in the Northern Hemisphere, and then it melted, and we entered a time period of the last roughly 10,000 years, which is the time period we live in today. And the message from this plot is that the climate system operates very slowly and that very little has happened in the last 10,000 years. This is what we thought to be true 20 years ago. And it is a very important thing because it means that if the climate system operates this slowly, that nothing that humans could do would in fact impact it. And if it did impact it, it would take possibly thousands of years. What we discovered was something that's quite different. We discovered that you could have massive shifts in storm frequency, storm intensity, precipitation, and temperature, and that these massive shifts in all of these things could occur in less than 1 to 2 years, dramatically faster than the thousands of years that we thought, and that they could be sustained for many decades to many centuries. This completely revolutionized the field of climate science, making it directly applicable to how we operate literally on a day-to-day and certainly on a year-to-year basis. The animation that you see is actually the day-by-day reconstruction for a particular year. This is 2012, of how wind patterns change over the surface of the Earth. And these very, very abrupt changes in climate, which happen in less than a year or two and are sustained for many decades, if not more, are basically the atmospheric circulation system being locked into perhaps a more northerly position or relative to the poles in the Northern Hemisphere, or locked into a more southerly position, effectively making winters much longer or making summers much longer. Once the system locks into that, it tends to operate in that system for a while. The other thing that we learned was how all of the things that control the climate system come together to create thresholds, in particular thresholds that could lead to very fast change. And the cartoons up here show you the basic things that control the climate system. In the upper left, insolation. This is the relationship between the Earth and the Sun and other planets that controls, on the order of many thousands of years at a time, how much energy the Earth receives from the Sun. But then everything with a red star on it are the things that actually can lead to abrupt climate change. These include elevated levels of CO2, depending upon how fast they increase, methane, nitrous oxide, the greenhouse gases, changes in the amount of energy coming from the sun, which can occur during the solar cycle, 10 or 11 years, changes in dusts, aerosols, massive volcanoes which can shield the Earth, and then looking in the middle, changes in thermohaline circulation. This is the change in the heat transfer and in the salt transfer throughout the ocean, and ice dynamics. Large ice sheets, even as large as the Antarctic ice sheet, 1.5 times the size of the United States, on average 2,000 meters thick, can change in its aerial extent quite quickly, leading to massive outbursts of sea ice, which cover the ocean and change heat exchange. So those red stars are climate controls which can come together to create threshold situations that in the past, in the natural system, have created abrupt climate change. But I'd like to bring the entire story much closer to the Middle East. Obviously, that's one of the primary purpose of this conference. But of course, to talk about the Middle East, we need to primarily think about precipitation. And if we are considering precipitation, as everybody here knows, winter precipitation throughout the Middle East winter is the time of dominant precipitation, summer less precipitation. So in order to take this 110,000-year record and relate it to something in the Middle East, it's important to relate this record as a way to find out when in the past were winters longer, when were summers longer. So we've been able to do this going back, but we focus primarily on the last 10,000 years because it's the last 10,000 years that civilization has emerged. And again, if we take a look at something that tells us about the length of the winter, in this particular case, it's the extent of North Atlantic sea ice as determined from records in Greenland. More sea ice means winter dominates, which means that the Middle East will have, in general, higher precipitation. Less sea ice means summer dominates, it's longer, and therefore the Middle East gets less precipitation. If you look in the center of the diagram, 4,200 years ago is the most prominent event in this record of the last 10,000 years. It's a critically important event to the Middle East because 4,200 years ago was the height of the Mesopotamian Empire, modern-day Syria, Iraq, into Iran. And 4,200 years ago, there were longer summers, which would have, of course, absorbed more precipitation, allowing it not to fall on the ground. But there was also a massive shift, a couple of degrees latitude north of air masses that bring in wind. This led very, very quickly, certainly substantially, to the collapse of the Mesopotamian Empire. The same can be said for the collapse of the Mayan Empire about 1,100 years ago and several others. So there is little doubt that large regions of the world can experience very, very small changes in the position of moisture-bearing winds and temperature leading to dramatic drought. It happened right here, 4,200 years ago. So let's return to abrupt climate change. That was an abrupt climate change. It occurred in less than 5 or 10 years. What are the things that humans can do to intensify abrupt climate change? They're the things that are circled. The solid circles mean things that humans can absolutely impact. Obviously, greenhouse gases, dust levels from aridity, agricultural activity, and also changes in ozone level. Turns out that when the sun emits energy, one of the mechanisms by which it changes the Earth's climate is to change the amount of ozone in the upper atmosphere that protects us. When humans begin to impact the climate system through changes in ozone, changes in dusts, they also change the amount of water, fresh water that goes into the ocean, which changes heat exchange throughout the ocean, and they can also, as we know already, through heating, impact the amount of ice on the planet. CO2, greenhouse gases in general, in the Northern Hemisphere are the most important change. And it is not only important that over the last million years, levels never got above 280 parts per million per volume. Currently, they're at 400. But what's even more important is the fact that in the case of CO2, the levels have risen 100 times faster than they have in the last 800,000 years. And that's only because we have records going back 800,000 of years. I would dare say that the levels have risen 100 times faster than perhaps they ever have in Earth history, certainly in the last million years. This suddenly makes the forcing of abrupt climate change by greenhouse gases a reality. So, as the world begins to warm as a consequence of rising greenhouse gases, it doesn't warm evenly, and this is where some of the complications arise. This is a plot showing roughly the last 10 to 15 years of warming relative to the previous roughly 20 years. This is using what's called climate reanalysis data. These are data sets. There are many different types of reanalysis. This is probably one of the best trusted for this area. It's put out by the European administration. And you can see that in the Arctic, the high Arctic in particular, temperatures have risen the most in the Northern Hemisphere. And in addition, in parts of the Middle East, some of the temperatures are of the highest in the last 3 decades. But there's a big difference. Not all of the Northern Hemisphere has warmed. If you go to the mid-latitudes, they haven't warmed as much. And this creates a temperature gradient. And once you have a temperature gradient like this, which is cold areas actually getting warmer, what you do is the temperature gradient is no longer very steep from the poles to the equator. It begins to flatten out. And the net result is that the position of the winds migrate closer to the polar regions, and the strength of the winds obviously sometimes will be reduced. This is extremely important in where heat and moisture is delivered throughout the Northern Hemisphere. So let's first take a look at the warming effect of its relationship in the Middle East. If you take a look at a correlation between temperature and precipitation in the Middle East, when temperature goes up, precipitation goes down because warmer air obviously can absorb more. And if we take a look at the generalized change in temperature over the period 1979 to present, which is when we have the best temperature records around the world, this is from the climate reanalysis data, we see that in general for the Middle East, this is annual record. As you begin to look, for example, at individual months, more and more information emerges, but in this general sense. As of about 1998, throughout the Middle East, in general, there has been about a 1 degree centigrade rise in temperature. This is a very, very fast, dramatic rise. Along with that, it's been about a 40 to 50% reduction in moisture throughout the Middle East. If we take a look at the projections for the future for the Middle East, on the left-hand side, the projection for 2030 to 2040 for temperature is that by then we will experience a 1 degree centigrade rise. Remembering that as of 1998, we've already experienced a 1 degree centigrade rise. So a 1 to 1.5 degree centigrade rise by 2030 to 2040 is actually not a very, very big increase in temperature for an area that responds so reasonably. So perhaps the models are underpredicting. If you take a look at precipitation, the models predict by 2030 to 2040, relative to the last 10 years, a drop in precipitation of about 10% to 15%. Remember that in the last few years since 1998, the Middle East in general has lost 40 to 50%. This could again be an underprediction of how the system will operate in the future. The atmospheric circulation effect, this is important because the direction and the intensity of moisture-bearing winds are critical. That's what led to the collapse of the Mesopotamian Empire 4,200 years ago. And if you take a look at surface pressure, which is one way of understanding where the winds go, you find out that as surface pressure over the Middle East decreases, precipitation decreases. And if you look on the right-hand side, that large purple mass over the Middle East suggests that there has been not a large, but a small drop in surface pressure, and therefore there should be an accompanying drop in precipitation. This is what that same animation that I showed you before looks like over the Middle East. Air masses that deliver moisture and heat come from the west, sometimes the east, sometimes the north, and often the south. If they go over water areas, obviously they transport more water. If they go over dry areas, they lose their moisture en route. So trying to understand how these wind patterns have changed in direction, intensity, and latitudinal position is important. It turns out that for the Gulf region, since about 1979, we again have a dramatic change in 1998. The zonal winds, which go from west to east primarily, and sometimes east to west, have actually become less variable, and if anything, they've become more easterly than westerly. And the so-called meridional winds, the winds that go from south to north or north to south, have clearly declined since 1998. And obviously, when they go over water-bearing areas, this is critical. When they go over land areas, they bring nothing but dry air. Something very, very big happened as of the last 10 to 15 years in the Arctic. It is the first abrupt climate change created by humans. It's the first of many abrupt climate changes that we should expect for the future. The important thing here is that these abrupt climate changes are not necessarily taken into account in the models. It's very hard to take them into account. You can't model them easily, but one needs to understand that they're there. In the Arctic, this abrupt climate change is represented in the last 5 years by a 5°C rise in temperature and a doubling in the length of the summer. This is on an annual basis. Based on our calculations, looking at records in detail, this is as extreme a warming as has occurred in the last 12,000 years. It's over a much more localized area. 12,000 years ago, the warming extended over much more of the northern hemisphere, but this is potentially the first of many such events. So if we look a quick summary, and if we take a look at Arctic sea ice on the bottom, going from 1979 to the present, big change, certainly by 2000, a declining trend going back several years. It aligns with changes in zonal winds, meridional winds, precipitation, and temperature, all of these things. It tells us that the wind systems in the equatorial latitudes, in the temperate latitudes, and the polar latitudes are all connected. And as the Arctic begins to melt, wind systems, just as they did during the collapse of the Mesopotamian Empire, will move farther southward. So it becomes critical to have several different ways of thinking about how the future will emerge. On the far left in the blue is a linear projection, which is what the Intergovernmental Panel on Climate Change uses. This is a perfectly logical thing. It's based on the last, basically, 30 years of record. If you look back farther, however, you find abrupt climate changes. And these have a dramatic impact on water, health, extreme events, and also sea level, which is what I'll end with here in the next couple of moments. Sea level also has potentially been under-predicted. If you look on the left-hand side, you see the projections in the last Intergovernmental Panel on Climate Change for the period 2100. IPCC suggests a minimum of 6 centimeters, as much as 98 centimeters by 2100. There are other studies, one conducted on Antarctic ice masses that suggests perhaps 1 meter and 40 centimeters by 2100. If we look on the right-hand side and look at the geologic record, it's an imperfect record, but it certainly broadens our perspective about sea level change. We see that the last time the temperature was 2°C higher than it is now was about 130,000 years ago. That alone is quite a remarkable fact. And at that time, sea level rose 4 to 6 meters. Now, 2°C is in the lower range of expectation from the IPCC for 2100. If you take a look at 3°C rise by 2100, which is sort of in the middle to perhaps a little bit high, the last time that happened was 30 million years ago, based on the geologic record, and at that time sea level rose 20 to 30 meters. And the last time temperature was 4°C higher than today was 40 million years ago. So this begs the question, if sea level, in fact, from 2 or 3°C, based on the geologic record, as imperfect as it is, but even if it's off by a factor of 2, it's still critically important, how fast can these changes occur? And again, if you go back to the geologic record, this is work done by many colleagues over the last year, turns out that 14,500 years ago, as the Antarctic ice sheet and parts of the Greenland ice sheet were melting, sea level in a period of 500 years rose 20 meters. Obviously, that's the equivalent of about 4 meters in 100 years, significantly more than the IPCC estimate of 1 meter by 2100. Does that mean that we'll have 4 meters by 2100? No. But it means in the long term, by 2200, 2300, it would be really a good idea to think seriously about sea level rise on the order of at least several meters. It takes tens of years to relocate, to protect oneself against sea level, and this is an important extreme measure for people to be thinking about. So the Climate Change Institute, because of our ability to look back in time, has clarified the understanding of the dynamic range of the climate system. It's produced new analogs, and now we're beginning to depart into climate adaptation and sustainability planning that includes abrupt climate change. How do we do that? We do it through the development of what are called plausible scenarios. You take 4 different potential scenarios. One is a linear change in climate, another might be an abrupt climate change in climate by 2030, and 2 others. And you develop for the region an understanding of how these things might progress. Even if 3 of them turn out not to be correct, they make for a very, very good way to think outside the box and to think about what the potential will be. I can guarantee you that climate will not operate linearly. It never has in the past. It won't happen in the future. We've already had an abrupt climate change. So it is important to assume that things that we think will not happen until 2100 could very well happen by 2030 or 2040. Thank you very much.
Hi, I'm Dan Sandweiss. I'm a professor of anthropology and climate studies at the University of Maine, and I have the honor of moderating the upcoming panel. And I've asked the panelists to come take their seats as I introduce the panel. As we've seen, the world faces significant challenges related to water supply and water quality. To keep meeting these challenges, it is essential that we produce a new generation of water researchers at the cutting edge. People who will have this incredible imagination that Tom Parrish talked about earlier today. I want to thank Dr. Jamal Al-Suwaidi for convening this conference, for inviting us, and for his vision, including this panel on water and education. Our first speaker in the panel is Dr. Doug Bousfield from the University of Maine. He is a professor of chemical and biological engineering. He received his Bachelor of Science in Chemical Engineering from Montana State University, his Master of Science from Oregon State University, and his PhD also in Chemical Engineering from the University of California at Berkeley. He has been on the faculty at the University of Maine for 28 years. He does research in the areas of fluid flow, rheology, flow in porous media, coating flows, and drying. He is also the director of the University of Maine Paper Surface Science Program, and he will talk to us today about low-cost water filters from carbon nanofibers. Doug.
Okay, thank you. Thank you, Dan, and thank you for the opportunity to share with others about some research we're doing at the University of Maine and something that we're fairly excited about, and something also that links to education, in that a lot of this work was stimulated and done by high school students. So I'd like to show you that. And we also want to share a couple ideas that might stimulate some solutions to these problems that we're talking about this morning. Yeah, so we've all heard many talks now already this morning about water shortages becoming more serious as climate changes. And we're thinking also not only about the scarcity of water, but storms like hurricanes or typhoons can really disrupt water supplies too. There are a lot of what I call high cost, or even we might even consider still low cost methods to clean water. But we're excited about this one material that has become available. We call it cellulose nanofibers, that are a low-cost material that might be able to lead us to a low-cost water filter. And so maybe a slight correction to our title in the program. These are cellulose nanofibers, not carbon nanofibers. So water supplies, and we've been talking about many issues around things. It's the only option for many people are surface water, and especially in some developing countries, countries that don't have much infrastructure, countries that don't have a reliable electrical source, the only supply of water might be like what's in this picture here, gathering water from some open source. And as you can see from this picture, doesn't look too good. And we wanted to think about ways, so this is maybe not applies directly to UAE in this situation, but helping others in countries that do not have access to technology, electricity, and things in this manner. This also, I think, illustrates a point that I think is important too, is when I work with students, it's always good to have a big picture in mind, and definitely helping others in other countries is a real motivating factor for a lot of students. They want to make a difference. So I know people in this audience are in the same boat. We want to make a difference. So countries that have good energy sources, this is not a problem. And USA or UAE, no problem. We have ways to purify water, resources to do that. We have other ways to use reverse osmosis, multiple effect evaporators, multi-flash evaporation to desalinate water. Electricity is often tied to purifying water, and because it's needed for pumps and other operations. I want to maybe throw in one other idea. This is not really the main topic of this talk, but I wanted to, I was glad to see an earlier talk about solar desalination. But one topic that I might want to, we have some interest in here has to do with solar power desalination. And solar stills are one method that's well established, and for many hundreds of years, actually, this has been used to purify brackish water. There's a number of, if you read the literature, there's some solar concentrators that have been coming out where you use mirrors to reflect sunlight back to heat up oil or water to produce steam or to desalinate water. But we have some ideas around using what I'd call direct solar steam generation, and again, a very low cost per area of solar collection. So I like the idea of using solar power and solar, like photovoltaics, to generate pressure and generate, but those have a lot of inefficiencies, solar power or solar photovoltaic cells. This would have a very high efficiency to convert sunlight into water vapor, and then we can drive that, combine that with the multi-effect flash units or multiple effect evaporators and grab that efficiency that you get with that. Anyway, back on the topic. So high cost methods are clear, drill wells, purification systems, but even what we might consider even moderate costs are out of reach for many people. Here's just a list of some current, what we might call low-cost methods for people to purify surface water. And a lot of these things spring up, but some of them really, all of these have some serious drawbacks. I'd say, well, all this whole list here, the sand bed filtration is probably the leading candidate. That's been around and proven technology, but it's still not an easy method to implement, and it's not perfect. Chemicals at the bottom of the list, they also are well proven, very low cost, but chemicals are not always available, or the right combination of chemicals to purify water. So I want to introduce you to a fairly new material we call cellulose nanofibers. They're sometimes called other things in the literature, microfibrillated cellulose, nanofibrillated cellulose, or sometimes I see people just refer to it as nanocellulose. But basically, this material is produced in a simple way by mechanical action, grinding them, or a process we call refining, or another in the literature they call homogenizing, where you're just physically breaking these fibers up. And we're talking about wood fibers or other plant fibers. We can produce this material at a very low cost in our our pilot plant, and right now we can produce about 1 ton per day just with our pilot scale of equipment. Just for those that might know more about this, the cellulose nanocrystals, which are also described in the literature, are quite different than this material. These are very more expensive materials produced by chemical methods. So I'm only talking about the mechanically made cellulose nanofibers. This is what they look like. And if you take a close look at the picture on the left there is from an atomic force microscope. And if you look at the length scale bar on there, the whole picture is about 8 microns by 8 microns. And if you really look at some of the fibers in there, they're about 50 nanometers to maybe 100 nanometers. To put that in perspective, a normal paper fiber is about 30 microns. So a paper fiber would cover that entire picture on the left. So these are very fine fibers that are then are released by the mechanical action on these wood fibers. The picture on the right is a field emission scanning electron microscope showing the same material. You can see it's not a very pretty picture here. It's a pretty messy looking picture. Some people say it looks like spaghetti. But again, if you look at the length scale of those fibers, you can see, hey, this is a very fine material. And you can't help when you start to look at that picture, to think about, hey, maybe we could use this as a filtration media. Now, we were exploring the use of this material in a number of other applications in my lab, but I guess who'll speak later, Carrie James, was one that helped us get motivated to, hey, let's really spend some time and effort looking at the potential to use this as a filter media. And it's not so anyway, then how do we use this? And I'm just really briefly show some of the work that we've been doing. But how do we do this? We know we want to stop certain size of material, and things like Giardias or cholera or E. coli, those are not too difficult to stop. These are fairly large bacteria or other organisms. But even regular paper would have pores that are in the order of 1 to 5 microns. So even regular paper can't stop the bacteria. And of course, our goal might be to even stop virus that are in this water. And virus may be down to 50 to 200 nanometers. But if you look back at that size of the pores that we generate, we might even be able to stop the viruses by a filtration technique. So this body of this work, and I'll skim through some of the scientific detail here, but it's just to understand the flow rates that we get through these samples, these filters, and what size of pores we really seem to be capturing. And also being an engineer, we always want to be predictive. So really what we did here and some of the work I've been doing is set all of this to some equations so that we don't have to go through a lot of trial and error, but we can understand some of the flow rates we expect related to pores and capture efficiency. So I won't show too many equations, but a lot of the theory is based on what we call Darcy's law. It talks about the flow rate through a porous media driven by gravity. And we're thinking, again, of a simple, not a pressurized system where you need a pump, but a very simple system where you're just pouring water in, letting it filter out overnight. And if we combine that with some other expression for velocity, we can get a rate expression where h is like the height of water over the filter as a function of time. And maybe the key parameter in this whole group is the K, and that's the permeability of your filter. And we can predict like how fast it takes to filter something as a function of time based like on filter thickness. And here these are 3 different thicknesses of paper, and we pick a value of K, and we can see, as you would expect, a thicker filter generates slower flow rate, so the time to drop the water level to a certain amount is increasing. And we can compare different permeabilities. And here's now, we're going to start to look at a bucket filter where we start at about 600 millimeters high, and just how much time does it take to filter a bucket? So we're kind of thinking about designing a filter. And one last thing, a last equation in this talk is how do we relate K to the pore size? And this well-known equation in the literature called Kármán-Kozeny equation that helps us do that. And the dP in here is the particle diameter of your solids, and we know that that is often linked to pore size. So 1/3 of dP is often the pore size that you're probably generating. And here's what now we can start to say, what permeability might we expect for a certain pore size that might stop like bacteria? And let's say if we want a pore size of 1 micron, that would probably stop bacteria, and we have a certain void fraction of paper, which is normal, 30%. Oh, we'd get a permeability of 0.1, and the units of that would be 0.1 times 10 to the minus 14 meters squared. So it sounds like a very small number. Well, it is. And you can see, though, now the rate of filtering is critical here. Also, we don't want to design a filter that maybe blocks everything, but it takes forever to get any water that's of use. So look, if you want to stop virus, boy, you have to be way down there, and that's a very small value for K. And again, I'll skip through here. How much time does it take to filter water from our bucket filter? Here, it looks like to capture bacteria, it looks like 8 hours, like overnight would be a good time. And again, some other calculations around if we had different thicknesses of that material, yeah, we could get this capture of bacteria down to a few hours. But then we throw in the numbers for virus, man, even to filter 1/5 of the bucket, it takes like 10 hours. Oh, wow, that's too long to wait. That people need water quickly. So by manipulating the thickness and going to what I'd call a multi-layer design, we might be able to get into a region where we have just a thin layer that's doing the capturing and a thicker layer of filter media to capture or to give you the strength that you need. So, and the last thing I want to point out is there's this well-known phenomenon we call self-healing, and that as fibers might come down onto a filter or a filtration unit, if there's regions that become highly saturated with fibers, those are going to be low flow rate regions. And so by natural methods, more flow will be directed to the low regions, and then you generate a more uniform, filter media. This is basically, we're clogging the pores up. So sometimes we like this to happen, but other cases we don't. So finally, we came up with this kind of system where we have a funnel bottom, a paper towel that has wet strength properties, mechanical properties, but it's very porous. And a regular paper towel would not stop bacteria or maybe even giardia. Then a paper layer that's finer pores, and then a very small nanocellulose layer on top of that, a very thin layer, and a towel. And then we studied the flow rates through this system. And if we plot the data in a certain way, we get a really nice linear correlation. And even with crude taking of data, we get a very good correlation coefficient. But now from the slope of these lines, we can start to get our permeabilities, and we can see even just different kinds of paper have different slopes. So copy paper, that's the white paper you might copy on, that's quite open, porous, and we have very high slope there. Newspaper, or what I call magazine paper, has much lower slopes, lower permeabilities. Now we add to these papers the nanocellulose, and then the whole question in designing this, how much should we add? If we add too much, our flow rates through the system are going to be way too low. If we add too little, we won't stop material of interest. So anyway, again now, one thing that we've learned though from this whole study, and this is maybe a key point, is that the drainage rate itself could be a measure of the validity of your filter, how well it's going to work. So here we're adding nanocellulose to this paper towel, and we see as we go from little to more nanocellulose, the slopes drop, so our permeability is decreasing, but our capture efficiency is now increasing. And here's again just more data. But these are now starting to get very low flow rates. We did the same thing for, and here's how the permeability of the system changed with the amount of nanocellulose that you're adding. And then we did the same thing for newspaper. As you add this nanocellulose, the slopes of these lines decrease, but you are now becoming a very good capture membrane for even very small materials. Here's last set of data where, again, we can now tune our filter to get either flow rate or pore size that we really want. So that's maybe the message here. We're able, by changing the amount of this nanocellulose that we're adding into the system, we can tune the flow rate and pore size of these filters. Okay, so results is that this system seems to be quite good. Oh, I forgot to mention the towel on the top and bottom are just more to protect this filter from the bottom mechanical stresses. And the top, when you pour water into the bucket, you don't want to wash the filter, the surface clean. You want to protect that nanocellulose layer. And these systems now, we put in probe particles. They're just latex spheres. And we can see what size that these filters are able to block or capture. So last thing, how would we deploy something like this to a third world country? One idea is we'd produce the 4-layer system, and we would print on that system the method to use the filter. And all we'd provide, though, would be the filter. And we could provide this at a very low cost. I mean, pennies per filter. So when they're used up, they would have maybe 100 of these filters per person. Costs, again, could be covered by a charity organization. The other way, we could actually buy because this is just this nanocellulose, it sounds fancy, I know, and we use big equipment to make it, but this is something that actually people out with very little means could actually make by physically grinding wood fibers or grass fibers by hand. And so we could instruct and teach people how they could do this on their own. So it's not, again, something that requires a large amount of resources or things, but it does take knowledge. It does take an understanding, because if you just try this randomly, like we did a few years ago, we had poor success. We first generated filters that didn't capture anything, and then we generated filters that wouldn't let water go through. So it's a very fine balance between getting that right amount. Okay, just summarize that this new material we're not there yet. We still have more work to do, but it has a lot of potential to generate these low-cost water filters. Another key point is we have the potential to tune these filters by the addition level of the nanocellulose. One best method is to form the filter by filtering the nanocellulose, because it naturally will clog the large pores. And this should be a cost that's much lower than all the other methods that are out there right now in the literature. And last point is that we can use the flow rate we get through the filter to kind of probe whether that filter is viable enough. If you're getting too much flow through it, you likely have some large pores. Okay, I appreciate our sponsors, and I also want to publicly acknowledge Kerry James, who will speak later, for his encouragement and motivation on this whole topic too. And I thank you for your attention.
Our next presentation is by Taha Kwarda, who is professor and head of the iWater Center at Masdar Institute of Science and Technology. He received his PhD in water resources from Colorado State University. Until 2011, he was the head of the Canada Research Center on Hydroclimatology and the Hydro-Quebec Industrial Chair in Hydrology. He's published more than 350 papers and refereed international journals.
Thanks. Hi, everyone, and I hope you're going to find this talk of interest. So it's going to be relatively simple. I'm going to be presenting some ideas about research directions of interest in this region. Naturally, I'm a bit biased to my field of research, but in this case, I believe it's a field that's not getting enough attention. We'll get to that. So I believe the statement of His Highness summarizes the situation when he said that water is more important than oil in the UAE. Basically, it's the long-term viability, sustainability of life in this region. If we look at the water challenges in the region, the first thing is scarcity, basically. UAE is one of the countries with the lowest amounts of water, natural, renewable water, so rainfall mainly. At the same time, it has the highest, probably, as far as I checked, the highest per capita water consumption in the world. Several times the consumption of countries that have large amounts of water, like Canada, for instance, or Germany. So we see already that work needs to be done in two directions. Increasing supply, so finding sources of supply for water, but also decreasing demand. The issue here is that things are going to keep getting, in a certain sense, more stressful as the water demand is projected to increase by 50% in 2020 because of the population growth, industrialization, basically more demand from different sectors, urban sector also. So we need to ensure that we have the necessary supply, not for today, but for the future, and change is happening very quickly. We're going to be talking a little bit about climate change also. How does actually climate change affect this region? Other things enter into play as we have nuclear energy now coming into basically the grid. That changes some of the data because in the past we had a situation where we had cogeneration plants. So water and energy were more linked than anywhere else in the world. I mean, we speak about the water energy nexus. In this case, basically you're generating both at the same time. So in the summer, typically we have big demand for cooling, for energy, so we end up producing more water than necessary. It's the energy that drives the system. In the winter, it's the opposite. Energy demand is not very high, and it's water that's driving the system. So we're thinking about where can I store the water in the summer, because I'm producing more than I need, and then the winter is the opposite. What can I do with the energy? That situation is going to be changing as we move away from thermal desalination, from cogeneration, into basically new technologies, membrane-based technologies mainly. Then there's going to be a decoupling, in a certain sense, of the energy and the water. And that creates a whole new situation which we need to address. So the topics that seem to be basically the focus are desalination on one side and water recycling and reuse. That's to meet the demand, to provide basically the water that is required. And then improvements in water resources management to try to reduce the demand. Okay? So meeting the supply and reducing the demand. These are the directions in which we should be focusing. So, and as always, a challenge is actually an opportunity. If you meet the challenge, you develop the expertise, and then you actually can benefit from that. We have here a great opportunity to develop technologies that are homegrown, that are developed to meet the needs of arid regions, and then why not, we can become exporters of technology to other countries, basically, that have similar conditions. So it's actually an opportunity to become the owners of some sort of knowledge that has value and that can be exported. Okay. So the research in the water sector in the Gulf region, the UAE and the Gulf region, the objective is really to provide the science and the technology. And I insist on both words because we often think about the technology. When we speak about desalination, when we speak about water treatment, water reuse, it's technology. And the science often gets a bit neglected. The second reason that this happens is that the private sector is often interested in investing in the technology part because there is benefit to be made. If you develop a new membrane, if you develop a new protocol, you can market it, you can make money out of that. But working on developing procedures to optimize the use of the water or to basically minimize the waste is not something that the private sector is interested in. The private sector is more interested in increasing, actually, the demand. So when we come to the science part, the government needs to step in more frequently, while in the technology part, the private sector can assume a large part of the weight. So the objective is to develop the science and the technology to meet these challenges in our region. And the outcomes are very, numerous. Guidance on future technology, on future policies, as we were speaking for governments, development of these technologies, improved water management. The outcomes are very, very large and very strategic. And one large outcome also is quality, protection of the environment. As we find ways to use treated water more efficiently, then we're going to be putting less treated water into the Gulf and minimizing the impact. The treated water is very rich in a number of basically nutrients, and that has a large impact on the Gulf water quality. So there is always an environmental impact also that is important. So if we look at a shopping list very quickly of the topics in each one of the thrust areas. So we have 3 thrust areas: desalination, water and environmental technologies, and then water security. That's really the science part. We have a number of techniques that are of interest in the desalination part. Reverse osmosis, membrane distillation, forward osmosis also, and then hybrid technologies that combine different approaches, thermal with membrane techniques. Then we need to look at what we're going to do with the brine. How do we treat the brine? How do we deal with it? How do we treat the water so that the membranes are going to work efficiently? So how do we deal with the fouling of the membrane? As the membrane works, basically, we're going to have the impurities that are going to stick to it, and it's going to become less efficient, so you need to clean it. How do we do that efficiently, minimize the use of chemical products and all? And the post-treatment also, not just the pre-treatment. There are very interesting questions that can be addressed over here. And I believe that quite a bit of attention is already going in this direction. But what we need to realize is that we have often to think locally, the homegrown solutions. How can we rely on local products to develop original solutions? I'll get to this. I'll get back to this basically in a few seconds. Then we have the water and environmental technologies thrust, where we have things that are related to wastewater reuse and recycling, the biological treatment processes, modeling the risk, anaerobic fermentation, biofuel production. So here we go back into the water energy nexus, where we cannot actually separate treating water from the energy that could be produced and that has sometimes even more value. We need to look at both at the same time. Modeling brine discharge. Then we get into impacts like red tides in the Gulf. I'll show a picture afterwards of an event that we had recently, and these can be very serious events when we have red algae blooms in the Gulf, and they affect our desalination plants. So they affect our security in a certain sense. Modeling coastal water quality and ocean health in general. Then we get into the science part. That's not technology. We can call that water security. We have all the management part, doing the appropriate budgets, understanding where is water going here, where is it coming from, and how can we balance our budget more? Because our budget is not balanced now. It's not a natural budget. It's desalinated water that's dominating the budget. Looking at the impacts of climate change and its impact, not just as far as water availability, which is the overall picture, but as far also as the extremes. The risk associated to climate change, even if the mean may not be changing, if the variance is changing, I'm going to be getting more extremes on both sides. So upper tail and lower tail, and those need to be managed. Think floods and droughts. Modeling population growth and how it's going to affect the demand. Then we have all the sensing parts, including remote sensing, that needs to be developed. A large number of these activities can be handled by acquiring remotely sensed information. If we're looking at modeling the water quality in the Gulf, that's something that can benefit from satellite images. And we can get a lot of information that can feed directly into our models. So we need to work on developing all the monitoring part and the sensing part. Then we need to develop the mathematical tools to model how things are going to be evolving into the future. The evolution of hydrological meteorological variables. Basically systems analysis component, and also trying to understand the leak detection and understanding how we can improve this. When you look at the rate of return of water in the UAE, it's around 25%. That's basically the percentage of the water that's distributed in the system to the domestic environment that ends up finding its way back into the treatment plant, into the sewer. So we have a large portion of the water that's being used outside, washing cars, watering lawns. And how do we deal with all that? Because that water is actually, in a certain sense, wasted. Water that goes back into the treatment plant is water that we can reuse, okay? So I'm gonna go very quickly through this list. Reverse osmosis, all the techniques that are related to reverse forward osmosis for post-treatment, pre-treatment. There is a very large number of techniques that can be dealt with, and what's more appropriate, for instance, for Gulf water or for the Gulf of Oman water, which is less saline, where each technology can be used more efficiently, which one has more potential in different region. Same thing when we go into membrane technology. We're looking at the energy consumption also, where things can be used appropriately. How do we integrate renewables in here? Which technology will handle that more efficiently? And then all the issues related to not just the treatment itself, but the pre-treatment and the post-treatment. So there is really a wealth of topics here that need to be addressed that, I mean, each one can represent several PhDs. A lot of work needs to go into this. Thermal desalination, although we're moving a little bit away from thermal desalination into the future, it still represents a large, the bulk of our system now, and we need to address it, and we need to look at how we can develop hybrid models. Integration of renewable power, the UAE now is taking a leadership role in the integration of renewables in desalination, and there is a lot of work that can be done over there. And again, that's an aspect where we have the nexus, the water energy nexus, that's very present. So something important here is that we cannot address water issues in this region while ignoring the energy issues. They're very much coupled. And we need to develop basically teams that can address both at the same time. I'm going to skip this membrane technology. Basically, my colleague right before me has presented more detailed things of interest. So the last picture you see the membranes that can be developed from starch that some people are looking at, so renewable material. I'm going to go into the water and environmental technologies thrust. So wastewater recycle and reuse, the bioremediation aspects need to be addressed, the management of a number of pollutants. How do we use the treated water? Right now, we are putting a nice proportion of the treated water back into the Gulf. That water has value. We can use it in a number of applications. Aside from landscaping, we can go into irrigation, but there are other applications. We can use it in industrial systems. We can use it to fabricate concrete in construction. How can we give more value to that treated water rather than lose it by putting it back into the Gulf and dealing with the environmental impacts of discharging it? Recovery of energy, again, water and energy. Treated water has a lot of energy. How do we recover that energy? Biogas considerations, when we're dealing with anaerobic fermentators, for instance, how can we improve them to be adapted to our region, to our climate? A lot of work needs to go into these directions with very high potential. Then the coastal water quality, we spoke a little bit about red tides, forecasting modeling, but there are other issues. If there is an oil spill in the Gulf, it's gonna basically endanger all our desalination plants. So tracking water spills, monitoring them and modeling their evolution, where's the water gonna be moving, these are important things that need to be looked at. And also we need to be thinking about the intakes of these desalination plants. Where is the best place to put them so that they're not affected? Where should we discharge the brine so that it's not going to affect the environment around the intake? So all these things deserve a lot of attention. Then we have a number of topics that are related to basically modeling the health of the Gulf, developing a number of tools like hydrodynamic models to understand the movement of the water of the Gulf, what's the residency time in different locations, which places have more stagnation, and those tend to happen near the coast, near the desalination plants. All this has a lot of potential in improving the way we operate these desalination plants. I'm going to skip also through this, since my colleagues have talked about this before me. So some of the activities that could be of interest. We've been playing with these polymers, the concept of solid water. Solid water basically consists in using these powders. It's a type of powder, it's a polymer, that when you add water to it, it becomes a gel. Now the advantage of having this gel is that water that is in that gel is not going to be lost by evaporation, it's not going to be lost by infiltration. When you put that gel near the roots of the tree, for instance, the tree is never going to suffer from water stress. It's always going to have exactly the right amount of water to take over a long period of time without the water being lost by evaporation and infiltration. So you reduce the amount of water that's being used and you increase significantly the productivity. Okay? So this is something that we've been playing with. I mean, I don't have funding to work with this. We're doing it really out of pleasure. And here we're looking at the use of these polymers to produce cucumbers. And we tested also how we can use treated water. And basically with the same energy, with the same time, we're doubling the productivity. And we tested these cucumbers like any product that's going to go in the market, and it's safe. We did the testing in Dubai. and it's safe. Doesn't have any heavy metals or anything. So these are directions that could be really of interest, and they're directly of interest to us over here. We have poor soil, we have lack of water, and we need to deal with these conditions. So we need to be working on these water retainers, these polymers. The water security thrust, very quickly, as I said, a lot of interest in modeling the budget and balancing the budget. And that goes through understanding all the components of the budget and seeing how we can reduce the consumption, what's the renewable part, and how can we basically balance it in a very optimal way. A lot of work can go into this because we do not know actually what's really going on. Groundwater, there are thousands of wells, but we do not know exactly how much water is being pumped, how much water is being used in agriculture, okay? Let alone afterwards improving the way we use that water through novel irrigation systems. For instance, like I was mentioning, the use of solid water, these polymers. The work on modeling the hydroclimatology in the region. What are the drivers of the climate in the region? What explains the variability of our climate from one year to another? What are the long-term trends and what's driving them? And it's not just about rainfall, it's about all the variables that end up affecting the water field. Temperature. My colleague before was explaining the link between temperature and precip. Humidity, wind, all these variables need to be modeled, and we need to develop an understanding of how basically they interact and what drives them, so that we can model the long-term evolution of our climate and the variability, the interannual variability. A lot of work needs to go into this. We have a very good understanding of how the dynamics work in other places in the world. In this region here, we still have a lot to learn. That's a topic that really requires a lot of attention. Environmental hydrology also, and then water management issues. I spoke about leakage detection and all. So these are things that really need to be focused on with the perspective of this region. What I'm showing here is work that got published recently, and we're barely starting to scratch the surface here. When I announced to my colleagues 3 years ago that I'm coming to the UAE, I had colleagues tell me, why? You work in the water field and there is no water in the UAE. There's never been, there never will be. Why are you going there? And I said, wait a second, I mean, there's never been, I don't agree with that. There is oil. What's oil? It's organic deposits. That's animals, plants that lived in the past. If there is that much oil, that's a proof that we had forests, we had a lot of life. So it's not true that there's never been water in the region. You have reserves, groundwater reserves. So the first statement about we didn't have water in the region is wrong. Now the second statement about the future, we're not going to have it. We haven't done the science. We haven't done the modeling. Let's do the work and understand how it's evolving. And when I arrived here, I mean, everyone I talked to was telling me that water is decreasing. Rainfall is decreasing in this region. And if you look at basically the plot all the way on the left, that's precipitation in Abu Dhabi International Airport. And if you run any trend detection procedure, it's going to show you clearly that we have a negative trend. Yeah, precipitation is decreasing, but there is more into it than that. When we went and ran a Bayesian change point procedure, it's a procedure that detects where we have changes in the system, not just trends. We ended up detecting that something has happened around 1998, 99. Now, if you model what happened before 1999 and after, you realize that actually, that's the second plot, that actually precipitation is increasing. It has always been increasing. It increased before 99. There was a sharp drop in 1999, and then it started increasing again, okay? So we need to understand the dynamics. Now, what's driving this? What's that change in 1999? If we look at the plot in the bottom, we realize that we have a number of climate indices that actually changed phase around 1999. The PDO, Pacific Decadal Oscillation, for instance. So we don't even understand yet the teleconnection component, which climate indices affect our climate here? And why even rely on climate indices that have been developed for other purposes, other regions? Maybe we need eventually to develop a climate index that represents the dynamics in this region. So this whole direction, we're barely scratching the surface. Then you look at the seasonality, all the way in the bottom on the left, I plotted all the events that happened before, extreme events, before 1999 and after 1999. And we see clearly that there is a shift in the timing. Extreme events are occurring much earlier in the winter. While before 1999, extremes were happening around February, March, April, now extremes are happening more around December, even as early as November, okay? So we don't know what's happening here exactly. This is a topic where we're barely scratching the surface, and a lot of work needs to go into this. I didn't speak about the right part. That's the long-term modeling of the evolution. That's really trying to do simulations to understand what's going on in the future. And we see the uncertainty. The width of those bands is the uncertainty, spatially and temporally. So we have a lot of work to do in this direction. Monitoring the water quality in the Gulf. We need to develop a good model for the Gulf. A model that handles, for instance, the interaction with the atmosphere, because it's the atmosphere that's driving the temperature of the Gulf. And if we neglect it, we're going to be deviating systematically. A lot of work needs to be done. The picture on the top right corner, that's the red tide outbreak in 2008. And we see the extent of that outbreak. I mean, that ends up affecting a lot of our activities, including desalination plants. So modeling the brine, the discharges, oil spills, all these here require a lot of attention. After all, where are we taking our water for desalination? It's from the Gulf. So dealing with the Gulf is actually dealing with fresh water. So it needs to be integrated in the overall picture, okay? I love this. This is the type of project that really integrates a lot of things at the same time. My last slide, okay? So this is a standalone greenhouse where you have at the same time in the upper part of the greenhouse, you have an intake of saline water. So you bring in salty water, you have evaporation, you collect the fresh water on the side because of the evaporation basically, and you have a desalination plant. The greenhouse now is acting as a desalination plant. So you have the energy component, you have the water component, and then you can do the irrigation in the lower part of the greenhouse, and you have the food component. That's the water, energy, food nexus, all in the same spot. These are the type of things that are relatively original that should emanate from our needs and our conditions. I'm looking at some work that deals with some microalgae that exist in saline water, in salty water in the region. And the indication is that these microalgae are very rich in biofuel, actually. So you can actually use these microalgae to generate biofuel. Etihad had the first flight ever that was 100% by biofuel that is produced here locally from Salicornia, okay? So this is a serious direction. Now, it gets better because the residues, once you extract the biofuel, are shown to be good feed to fish in fish farms. So we have the fuel, energy, the food, and the best part is that to feed these algae, you can use basically polluted water that's coming out of fish farms, shrimp farms. And these algae act as water treatment plants. So you treat the water, you produce food, you produce energy, and if you want to feed them even better, you inject CO2. So it becomes a sink for CO2, carbon capture procedure and storage. These are local things. Nobody else is going to do them for us. We have to explore what kind of microalgae we have locally, and we need to go do the research and see what potential they have. I'm going to finish with this. Thank you very much.
Our next presentation is by Kerry James. Kerry received his Bachelor of Science from the University of Massachusetts and his Master of Science from the University of Maine in chemistry for the bachelor's and plant and soil science for the master's. He's been a chemistry teacher for 29 years, the last 15 at Bangor High School in Bangor, Maine, where he is the head of the science department and the inventor of the STEM Academy that we'll be hearing about, and the mentor of many student researchers, including 2 national winners of the Stockholm Junior Water Prize. He is also a founder of Water for Me, which is a nonprofit group that works on water sanitation in Central America. In 2010, he was named the Siemens Teacher of the Year for Maine, and in 2013, he was named the New England Water Educator of the Year. Mr. James is going to talk to us about high school students as water researchers.
Well, good afternoon. Thank you for inviting me. I'd like to thank the Emirates Center for Strategic Studies and Research for this unbelievable opportunity to be here today. And thanks to all of you who stayed for my talk as well. So I'd like to talk to you, maybe a more appropriate title for me would be Blue Gold, the Bottom Line. We've heard so many talks today about the importance of water and water being the bottom line, the resource that we just can't do without. But I'd like to talk to you about 3 things today. One, you're going to see me refer to this word STEM throughout the presentation. That means science, technology, engineering, and mathematics. It's, I guess, the buzzwords for science, technology, engineering, mathematics as we proceed through, the next century and how we develop programs for our kids in schools. I'd like to tell you about the research areas and some of the things that we've done. You've already heard about a couple of them that my kids have been involved in, and how those research areas are incorporated into the STEM program. And then the last piece would be the scalability of this model. So this is a model that could be used anywhere in the world. This is an educational model that we developed in conjunction with the University of Maine College of Engineering that's applicable anywhere in the world. And we just heard some great examples of how research on water could be done. I couldn't have said it any better myself. So let's proceed. So a couple of recent water researchers. On your left is one of our students who actually did a project on cellulose nanofibers that Dr. Bosefield discussed. And she was the Maine State Stockholm Junior Water Prize winner for 2014, but she was also the State of Maine representative to the International Science and Engineering Fair, which some of the students from the UAE have been to. I got to meet the contingent from the UAE in Los Angeles at the ICEF competition back in May. And on the right, we've heard about pharmaceuticals being a problem in water. The student on the right actually used a process called synchronous scan fluorescent spectroscopy to determine the level of pollutants from pharmaceutical compounds and estrogen mimicking compounds that get into the water, which is a global water concern wherever we are. So some of the things that our students are involved in, this is Bangor High School in Bangor, Maine in the US. It's a public school, about 1,200 kids attend the school. And within that, we have a program called the STEM Academy, which actually has about 60 kids that are involved in research in science, technology, engineering, and math. Our students have been participants in a number of things. The Stockholm Junior Water Prize, my absolute personal favorite. I'm going to encourage the contingent from the UAE that's on the stage today that's going to speak to participate in this. It's a great event, and only great things come from it. The National Junior Science and Humanities Symposium, Andy Sandweiss is on the stage. Andy is one of my students in the STEM Academy. He's going to be graduating this year, and he actually was a presenter at the National Symposium the last 2 years. Quite an honor for Andy. The International Science Fair, ICEF, and the Intel Talent Search, to name a few. We've had a lot of kids go through these programs, and these are programs other than the National Science Symposium that your students can get involved in and should get involved in. So just some examples of the kinds of things. This is not all-inclusive, but just to give you a flavor for the kinds of things that my students have been involved in. These 2 projects were revolving around freshwater and wastewater. Wastewater is a major problem worldwide, and these two projects looked at the detection of pharmaceutical agents in water. I won't go into the details of exactly how they did it, but those are important areas of research for our kids. The next two projects are two projects that looked at a model that used a nanoparticle amplified immunoassay for rapid detection of E. coli 0157H7 or pathogenic bacteria in water. And these students actually developed a biosensor that was capable of detecting this. These two students both went on to the International Stockholm Junior Water Prize. I'll talk more about this later, and these are really just two phenomenal projects that the students were involved in. Cellulose nanofibers is a personal favorite of mine. I think this has tremendous potential. We have a student working on this. We'll probably have more than one. I think this is an area that you could also work on easily here, and we could probably transport some of this material to you. It's a great material because it's abundant everywhere in the world. All you need, as Dr. Boesfield mentioned, was plant material, and you can grind this up. Great potential is a low-cost water filtration system. So in Maine, kind of stepping back, in Maine we have kind of the opposite problem. We have a lot of water, and we're more interested in the sanitation aspect of it versus for you folks, you have less water, more interested in the conservation aspects, but there's a lot of overlap between them. And Andy Sandweiss will talk about water conservation as it pertains to climate change, and I'll leave that to him. He has a terrific presentation that he'll give following mine. So here are the core principles. I'm just going to kind of tell you the educational model that we've got and how it works. The core principles are a challenging curriculum that supports the research for the students. This is a key component. And this was all developed in collaboration with the College of Engineering at UMaine. Actually, Dr. Mohammed Musavi, who's not here, is a major player in this operation. An apprentice 3-year research mentorship. So our kids actually conduct research over a 3-year period starting in the sophomore year, and this is year-round school for kids. It's a novel idea. Kids actually work in the summertime in research at approximately a 6 to 8 week mentorship, paid mentorship. These typically happen at the University of Maine, but we have other industry partners as well. And some of them just work right at the high school with me. Focus on STEM, and a really strong relationship with the University of Maine. Now this program, for it to be effective, and this is a scalable model, you have to be within some kind of a close proximity of a research institution for it to work in the way it's designed. So I'll go into the mechanics of it here shortly. So this is it. This is the design. And as any school would have, you have a 9th grade, 10th grade, 11th grade, 12th grade year. And within it, there's existing requirements and there's new course requirements. And this was designed by myself and Dr. Musavi at the University of Maine. And the key component that typically is missing from a high school education is the T&E piece, the technology and engineering piece, which is the critical component of this program as it pertains to focusing on the research that the kids will ultimately do. So they really need a strong background. So on we go. So the way it looks in the summer of the 10th grade and 11th grade years, the kids enter a research mentorship. The 9th grade is open. We let them get in, get their feet on the ground. 10th and 11th grade is going to be a summer internship beginning in the summer of the 10th grade year. And then the research continues on through the 11th grade. This is a model that's not been used in our country. It's not uncommon to see programs that have a single summer of research, but to continuing over a 3-year period is a new thing. So there's support. There's the general requirements, which are important. In our country, English language, social studies, fine arts, all the requirements are met for all students, so our kids get that as well. And this is an accelerated program through science. We have what are called advanced placement courses. Typically, this might be called International Baccalaureate in many countries. The way I understand it, the school that the people on the stage go to actually have AP courses. So I learned something new today. So there's an accelerated program through the sciences. This is the mathematics progression. So what we do when they come in, we want to accelerate them in mathematics immediately. And the students typically end up in a combined 2-year math course that's done in 1 year. Now, it depends on the level of the student when they enter the program, exactly how that progression works. But the most common progression would be to go through this and end up in multivariate calculus as a senior. This is the T&E piece. So these are new courses that were developed, and we have what's called a dovetailed technology and engineering course. You see it on the left. And in the sophomore year, they learn MATLAB, which is very unusual at the high school level. So our students come out, for instance, Andy Sandweiss will come up here and speak shortly. He's had a MATLAB course. He's learned how to use it for data analysis purposes. He's gone through a Technology and Engineering 2 course, which teaches him computer programming using Python and Raspberry Pi technology. So they do a lot of programming in that respect. During the sophomore year, to your right, so the introduction to research methods would support the research that they're about to go into in the summer. So they will have had MATLAB and data analysis. They will have had an introduction to research, a research methods class, and then that'll segue them into the summer. Then they'll come back during their junior year, continue their research during the school year, approximately 2 to 4 hours a week during the year. Because these kids are really busy, as you can see from the strong academic schedule that they've got. Culminating in a capstone project, and not to put too much pressure on Andy, he's going to give you his capstone project directly after this talk. He's going to talk about his project. So that's the T&E piece, and that's new. That typically is not seen in a high school in the United States. But again, this is a scalable model, and this could be done anywhere. So if you kind of stepped back and took a look at it from the air, this is the way it looks. There's an existing curriculum on the left, on the bottom circle. There's a new curriculum on the right. That's all the new courses, the tech and engineering piece. And then all of that supports the apprentice research mentorship. And we've had a lot of great projects come out of this program. And you're about to hear one shortly. And one of the best pieces of this, the students go to the University of Maine, they graduate in 3 years with an engineering degree. And in our country, education is quite expensive, I'm sad to say. But this presents a significant savings for not only the families, but the student. And they walk out of the University of Maine with a degree in engineering and a job coming out, and it's a terrific program. So someone I'm really, really proud of, this is Rebecca Ye. Approximately 4,500 students enter what's called the Stockholm Junior Water Prize each year. They do research. Her project was the biosensor, the amplified immunoassay test that she developed. And she entered her paper in the Stockholm Junior Water Prize. It's a national competition. She wins her state, the state of Maine, which is where we're from. So you have to win your state. Then you go on to a national competition, approximately 4,500. I think it was 5,000 people that year entered. They select one project from the entire nation, and it was this one. So this is a terrific project. She's now in medical school at the moment, just graduated from college. She went on to the International Stockholm Junior Water Prize and finished 3rd in the world. I thought she should have won, actually. So a quote from the Senior Vice President of IT&T, who's the sponsor of the International Stockholm Junior Water Prize, is this work is just invaluable to secure the safety of our water. That's a key thing. I've heard it over and over again today, the security of water. Something we didn't think about so much in the past, but we certainly do now. So on we go. So what are the global water concerns that we deal with? Well, we've been hearing about them all day long. This is another student who stepped in. Rebecca graduated. I said there's still work to be done. Why don't you step into her project? This is Layla Musavi. She decided to continue on the path that Rebecca had gone on. Rebecca had used a piezoelectric model Layla substituted in a new carbon platform using screen-printed carbon electrodes to essentially do the same thing. So you can imagine like a glucose meter if you were a diabetic. Well, this particular instrument that she developed using the screen-printed carbon electrode would work a lot like that. It's just an antibody-antigen response that you can detect with a small meter that you'd be able to carry in the field. And she won the Bjorn von Willer Watership Scholarship. She finished second in the country out of approximately 4,500 students in 2011. And they thought her project deserved recognition. They sent her to Sweden as well. And I must say, the opportunity for me was great. I actually ended up having dinner with the King of Sweden as a result of Rebecca winning the 2010 prize, and I got to go to the Nobel Prize Hall, and it was phenomenal. It was a great experience. So what are the concerns? Sanitation and conservation are the two big ones that I'm particularly interested in, but I certainly am interested in all aspects of water research. Groundwater contamination, we've heard about it today, a major concern. There's a lot of areas of research that kids could get involved in with water. Pharmaceuticals, climate change. So the International Stockholm Water Prize Committee designates these as kind of the key areas of research for kids. So then we started to think about, well, you know, we want to get more kids involved, and in particular what we want to do is get, in our country, we talk about underrepresented minorities. So underrepresented minorities for us are girls. We don't have enough girls in the engineering fields, and we wanted to find out ways that we could engage them more. And also we wanted to bring in Latin Americans, African Americans, Native Americans. So what we did, we created a program around a pervasive environmental issue called stormwater. And stormwater is a major problem for us. It causes impaired streams. We wanted to teach the kids how to collect water quality data and analyze and model it, do stream surveys, ultimately ending up in watershed management plans and the public outreach in terms of education to their communities. So we brought in a group, 60 students from a wide variety of backgrounds here. And these students learned how to develop wireless sensor technology. So they built wireless sensor boards that we actually install in areas, in the urban areas of the state of Maine, and that data is transmitted back wirelessly. And then what they do is they take that data and they go through the progression of what I just showed you and create these public outreach education programs for their communities. So what are the solutions? I mean, well, I wish I knew them all, but I think education's the key. And I've kind of devoted my life to water education and creating these kinds of programs. We've heard about it a lot today, invent new water conservation technologies. Recycling of wastewater is going to be a huge issue, improve sanitation measures, and agriculture and irrigation are going to be a major, major piece. And ultimately, we want to make clean water available to people, and in my mind, we want to make it available to people at no cost. So this is a model that could be applicable anywhere in the world. It could be moved, providing, there's a caveat here, providing there's a research institution somewhere within striking distance so you could get kids involved in mentorship programs. So it would look different based on where you are in the world. And the gentleman who spoke before me probably gave you at least 100 ideas of how you could do that. So thank you for doing that. So in closing, I'd just like to say I've told you about our program, our STEM program. I've told you about the areas of water research that we're involved in, primarily water sanitation and conservation. And I'd like to just finish with telling you this is a really scalable model to any school, anywhere, providing a close-to institution that can provide some support. And this is just a sign. I was in northern Peru, in the desert area of northern Peru 2 summers ago, and I saw this sign, and it just stuck in my mind. You know, water is life. They realize don't contaminate the river. That's your source of life. And these are just some kids from the Summer Stormwater Institute that they're the future. So I think the key is to get to kids early. Some of the greatest ideas come from kids somewhere between the age of 16 and 19, where their brains are fully developed or at the stage where they're not afraid to come up with some new ideas and actually try them. So I'd like to thank you for this opportunity, and I'll turn it over to Dan Samwise.
Okay, our next presentation is by Andrew Sandweiss. He is a senior at Bangor High School. He is a member of the inaugural class of the STEM Academy that we've just heard about. He's been doing research for about 3 years. He does it related to climate change and agricultural systems in Peru, partly because he is half Peruvian and has spent his life traveling to that country on a yearly basis. He's also the president of the Student Council at Bangor High. He's a published novelist and has several other interests, but I will leave El Niño Modoki, a diagnostic study for Peru and beyond, to Andy Sandweiss.
Well, thank you. And I first of all would like to thank the Emirates Center for Sustainable Strategic Studies and Research, as well as His Excellency Dr. Jamal Al-Suwaidi, for inviting me here to the Emirates, and I'm very, very happy to be here, talking on my project as my father mentioned. So, I'll just give you a rundown of what I'm going to talk about today. I'm going to look at the regional context of Peru, the country of interest in this project, climate change, how it affects and causes problems for this region, El Niño versus El Niño Modoki, two climatic phenomena that actually affect Peru in various many ways, which I'll describe, the implications of such effects, and sustainable policy planning as a way to mitigate the effects of climate change. So I'll begin with regional context. Peru is a country located on the western coast of South America, facing the Pacific Ocean. And the coastline of Peru, which is actually the agricultural center of the country, is a place very similar to the United Arab Emirates. It's a very dry desert. It gets very little rainfall. And so as I said, desert conditions and low rainfall. But this picture right here that you can see on the right is the only reason why it's the agricultural center of Peru. It's because of irrigation systems that come from the rivers that come from the highlands, the Andes Mountains, to the right of, to the east of the coastline. These rivers flow from the mountains to the ocean, passing through the coastline, and thus people for more than millennia have been able to use irrigation systems to permit extensive agriculture to be grown here, turning this region into the agricultural center of Peru. But with the changing climate, there are problems that Peru faces in the very, very near future. As temperatures increase over the past few years and decades, there have been melting glaciers in the Andes Mountains. Now, glaciers make up to 40% of the stream flow in these rivers. And there's been stated that global warming will completely melt these glaciers, meaning that the river flow could be reduced up to 40% if their source, up to 40% of their river flow source, disappears. And this is one of the problems that is really not a good time for Peru, as the agricultural corporations in this region are using the water in the rivers to the maximum, to the point that the rivers during certain seasons actually have no stream flow at all, and there's no water to give to the irrigation systems, and this will only decrease that water. And so now I'll move on to El Niño and El Niño Modoki. These are two climatic phenomena that occur and affect Peru in different ways. Now, El Niño has been known for centuries to wreak havoc in terms of heavy rainfall, flooding, and erosion. And as you can see in the chart on the left, these are sea surface temperature anomaly charts, essentially how different the surface of the ocean is from their normal temperature. And on the left, you can see it for an El Niño between the months of January and March. And you can see that there's definitely a positive anomaly, meaning the temperature is increasing more than, it's higher than the normal temperature on the surface of the ocean in the eastern Pacific Ocean. And it's because of this that those effects I described earlier about the raining, the flooding, and the high stream flow rates occur. And now to the right, in the right chart, which is also an anomaly chart, you can see that the position of the positive anomaly is moved, it's shifted to the left, to the central Pacific Ocean. But in reality, though, El Niño Modoki has only been discovered in recent decades. And because of this, people don't really know the global effects of El Niño Modoki. There have been case studies in countries such as China and South Korea, but nothing's really been done specifically for Peru or really anywhere in the coast of South America. In China, though, it's been stated to increase droughts, while El Niño usually increases rainfall. In South Korea, where El Niño usually decreases rainfall, El Niño Modoki seems to increase it. So it appears that El Niño Modoki, when you compare it to El Niño, has almost an opposite effect. And so looking at Peru, it would be interesting to see if this follows the global trend or if it goes against it. And we can then see if the location of these anomalies actually influences the impacts of the anomalies. And so, essentially what we have here is a graph showing the monthly streamflow averages for the Chicama River, the largest river in northern Peru. And what I've highlighted here is the wet season, the most important season for Peru, because this is where all the water comes down and provides water to the irrigation canals, because this is where there is the highest streamflow. And so what you can see here is that we have the El Nino is the black line for monthly averages, and you can see that it's about 2 times the normal amount of streamflow, which is the blue line beneath it. And this is expected because El Nino brings rainfall, and people have known these effects for years. Now for El Nino Modoki, on the other hand, since people have only recently discovered this in the 1970s and 80s, people didn't really know the effects. But here in this graph that I produced back in 2013, you can see that the monthly averages for El Nino Modoki are much less, about half that of the normal streamflow rate, which goes to say that El Nino Modoki is causing streamflow rates to be reduced in the Peruvian rivers. Now this isn't good for Peru, as I say before. An up to 40% reduction caused by the melting of glaciers is already reducing streamflow. This is only going to hurt it worse, and if it couldn't be worse than that, El Nino Modoki, caused by global warming, is projected to increase by as much as 5 times compared to that of the conventional El Nino, and that is due to climate change, as seen in the paper behind it. And so that means that this is going to be an increase in frequency climatic phenomenon that's going to really affect Peru in a very negative way. But there are solutions, and I've identified the problem, and it's now important to identify possible solutions. And the solution that I've identified is prediction, being able to predict these El Nino Modokis and El Ninos before they actually happen. And so here we can see 2 charts, which you can see a blue line that remains steady, and then you can see after a short break, it almost looks like spaghetti. And what it is it's essentially, you have the anomalies, those temperature anomalies on the surface of the ocean, up into the current date. And then after that, there are several climate models that predict very different outcomes. There are several different models that use different methods of predicting, and that's why you get so many different outcomes over the months. But you can still see that while in both ones, in the left that's for El Nino and in the right that's for El Nino Modoki in terms of predictions, you can see that they do cluster around certain numbers. Like for El Nino Modoki on the right, you can see that most of them are positive, and by being positive, that means there's a good chance of an El Nino Modoki occurring. So you can use these techniques to actually predict these El Nino Modokis before they occur. And to further these predictions, you can see here a chart, an anomaly chart, very similar to the one I showed before, which is on the right, showing the period between August and October. And then you see on the right, you can see the period between January and March. And if you look at the streamflow differences in those little graphs beneath each, you can see that there's not much of a difference in streamflow. In fact, there's barely any streamflow at all during those months of August to October. So there's really no effect of El Nino Modoki on Peru during these months, but you can still see the anomalies occurring during these months. So essentially, you can predict El Nino Modoki 4 months before it actually hits and causes that great difference in streamflow, which you can see on that graph in the right. And so by using this, you can say to the farmers in Peru or to the people in Peru that, look, there's going to be El Nino Modoki, and that's going to reduce streamflow, and measures need to be taken. So this is called non-structural adaptability in the sense that it doesn't require money, and you can essentially tell them and new actions can be taken as the season ahead forecast can provide very useful information, which can lead to potential mitigations taken out by the people approved, such as crop production, water usage regulation, and the diversion of river flow. But of course, this isn't just for Peru. As I said before, the effects of El Nino Modoki are felt across the Pacific Rim. Peru is essentially just a case study within that context. And so you can say, well, if you know now that El Nino Modoki is going to happen 4 months before it actually produces effects, this can be used for the countries such as China and South Korea, which I mentioned before, so they too can plan ahead, making this use of prediction a global approach to solving the problems some of the problems that climate change causes. And so that is the conclusion for my research. I would just again like to thank the Emirates Center for Sustainable Strategies and Research, Studies and Research, who sent me on Etihad, the national airline, for the Grand Prix. And I would also like to thank all of my mentors, Dr. Shalene Jain, Mr. Kerry James, my father, Dr. Daniel Sandways, and Mr. John Kingelosi, and of course the Bangor High School STEM program. Thank you very much.
That's fine. Our final presentation for this afternoon's panel is by Alia Abdul Rahman and Asar Rizk, and they'll be talking to us about water recycling. They are students at the Liwa International School, which is as you see on the slide, the first sustainable green school in the UAE and part of Sustainable Schools Initiative across the region.
Good afternoon, everyone. My name is Ali Abdurrahman, and I'm a student at Liwa International School. My friend and I came all the way from Liwa International School in Al Ain to stand in front of you today and tell you how our school became the first sustainable school in the United Arab Emirates, following a specific strategies. So the best thing to start our presentation with is a verse from the Holy Quran that says, "And we send down water from the sky according to measures, and we cause it to soak in the soil, and we certainly are able to drain it off with ease." Normally when the rain comes, it's well distributed. Rain soaks into the soil and produces a rich soil that is ideal for farming. Also, other forms of water are snow and hail, which settles in high regions and mountains. Without snow or hail, the abundant flow of rivers would fail. Adding to that, as wonderful as the water supply is, its drainage. Without the drainage of water, we would have suffered from water flooding and water clogging, water floods and water clogging. But how grateful a man should be for Allah's unlimited gifts in the nature. Adding to that, Sheikh Hamdan bin Zayed said, "The future would be very challenging unless action was taken to reduce water consumption, which is among the highest per capita in the world." And based on that quote, my school, Liwa International School, had followed certain strategies to provide a healthier and safer environment for students, teachers, and staff, in order to stay committed to our slogan, which is "Together for a better future for our children." The first step towards a sustainable school was the implementation of green walls. The second step was the implementation of solar panels. And the third and the most important step is water recycling. So the implementation of the green walls was actually an idea of seniors 2009. They suggested an idea for their biology project, and it was to cover the school with plants, and this idea was implemented and converted the school from a conventional school to a sustainable school. And the plants cover a total area of 3,000 square foot, which is 24,000 plants placed into boxes that is installed on the walls. And also, the main purpose of green walls was to reduce the heat and cool the environment. Because, as we all know, that plants increase the levels of oxygen, therefore cooling the environment. Also, the implementation of green walls decreased the reliance on the air conditioning, which decreased the bills of air conditioning. But money wasn't the purpose. The most important thing was to teach our children and the students to care about the environment and always think green. It also makes the school look better, and it's even more beautiful in person. Thank you.
Good afternoon, everyone. My name is Ashar Rizq, and I'll be carrying out the presentation from now on. As my friend has said, that our school has adopted certain strategies to have a sustainable school, which is implementation of green walls, implementation of solar panels, and water recycling. Now, speaking of solar panels, our school, Liwa International School, has implemented 102 solar panels across the school's roof. Now, these solar panels, they generate about 78 kilowatt an hour as a result of 28,470 kilowatt annually. All this energy that is collected from the solar panels is stored into batteries that can be further used by the school, such as night landscape light. The main purpose of implementing these solar panels was to provide energy for irrigation systems, as well as to reduce the consumption of electrical energy. These solar panels, they are cleaned from dust every 2 days, and they are washed weekly. Now, the last and the third sustainable strategy was water recycling. To reduce the amount of water used by the school, our school has followed the 3 R's method, and I hope you guys are familiar with it, which is recycle, reuse, and reduce. Now, the first step was to recycle gray water. About 50 to 80% of the water collected from showers and baths was gray water, and about 30 to 20% was sewage or black water. Now, the main purpose of creating this grey water recycling system was actually, of course, to reduce water consumption, as well as to reduce the amount of chemicals that has been released to treat sewage water. And finally, to reduce energy by increasing plant growth. Probably a question that's popping into your mind is how grey water is recycled back in our school. It's actually quite simple. The first step that students from the Eco Club had to do is to collect grey water from showers, basins, and baths. The second step was the water had to go through 2 purification tanks. The grey water had to pass through the first tank, which has 2 water purifiers that cleans and treats the water, and then that cleaned water actually moves to the second tank so it can be used by the school for irrigation plants. Now, as my friend has said, that our school is surrounded by green plants. Those green plants, they require 5,000 liters a day. And the actual amount of grey water collected is about 4,000 liters. As a result, grey water's irrigation system requires 78% of the water required for the green plants around the school. Now, our school has not only contributed in recycling water, but it also contributed in reusing water and reducing water consumption. The first step for reusing water was actually water coolers. We have about eight coolers across the school. Now, every time the coolers are used, 50 to 60% of the water is actually wasted. However, that wasted water is not gone for nothing. It is actually directly converted to another tank that is directly used to irrigate trees and plants across the school. Moreover, a second step for reusing water was actually collecting bottles that was left by students after school. Workers would empty those bottles, and about 400 liters of water bottles was collected. And this water was either used for cleaning or irrigation systems. Another thing that the Eco Club students have participated in, instead of actually wasting all those water bottles, we have contributed to place 2 water bottles into a flush box, which would actually decrease the amount of water released. At the end of the day, as a result, 1,470 liters of water was saved daily. These are calculations that have been detected by students from the Eco Club. As a result, after the improvement, around 16,000 of water daily has been consumed. Before the improvement of water recycling or reusing water, the numbers have been much, much more higher. And percentage of water saved is 11.4% of the water total consumption. Thank you for listening, and have a nice day.
I'd like to thank all of the speakers in the panel for outstanding and very stimulating talks. I know we're running late, but I would like to take time for a few questions. Before we start, I would like to make one recommendation, since that is one of the functions of the panel. Having listened to the last set of presentations about high school researchers, high school water conservators, it's clear that there's a great opportunity for interaction between schools in Bangor, Maine, certainly, and here in Abu Dhabi. I hope that one outcome of this conference will be a continued dialogue and a productive exchange between those schools that might expand to other schools. At this point, we'll open the floor if there are questions.
I would like to ask Dr. Where is he? Taha, Dr. Taha. There has been some shifting. Dr. Taha, when you talked about gel, did you mean the soil conditioners? Did you mean?
No, it's actually a water retainer that's sold.
Water holding capacity material that you add to the soil to absorb 10 times or 5 times as much as its usual holding capacity.
Yes, now it's being tested in surgery rooms to absorb blood, basically, automatically.
It absorbs what?
Blood during the surgery, so that you don't have to keep drying all the time. So people are looking at other applications.
You put it near the plant, near the roots, in the root zone. You add it to the root zone. You add it to the root zone to hold more water.
Yes.
How much do you add per meter square? And is it economic? Because we found out that these artificial, the PVC and the VPMA and those material are very expensive to add for trees and for green vegetables and so on. Usually you add them only to small nurseries.
These are different products. They are not basically the products you add to the soil to increase its holding. These are actually different. These are different products. These are not the products that you add to the soil to improve their characteristics. This is really a different type of gel that people started playing with basically very recently. You can, very little gets lost. As the roots basically take the water, the gel dries out and you can recharge it. So what we tried is putting a tube, and you can recharge the gel with that tube and it fills with water
Charge
again.
it with water?
Yes.
Well, then how much do you pay, let's say, per dönum or per square meter or per hectare? How much do you pay money to buy this material?
It comes in a small bag that costs us around $20. It's
$20, and it covers 1 dönum, 2 dönums, 3 dönums?
about 50. What we tried is putting just a few grains in a glass, added the water, it filled the glass with gel. So the whole experiment for the cucumbers, we ended up using a small fraction of a bag. And we had 2 greenhouses where we were testing different types of water, different type of soil, different basically approaches, salinity levels and all. So it's actually very efficient. Now, we cannot answer all questions before we do the work, actually, before we do our homework. Using this kind of product for trees, for instance, is going to end up being way more expensive than using it for tomatoes or cucumbers. But we need to do our homework to have the answer.
Well, I have another question, if I may. It is a question that nobody can answer, especially myself. We talk about sustainability and planning for climate change effects and drought and. Considering that the Arab world and the Middle East and North Africa gets about 65 to 70% of its water from outside. Jordan, from Syria and Israel, and Saudi Arabia shares an aquifer with Saudi Arabia. Iraq from Turkey, Syria from Turkey, and so on. How can we plan to combat and sustain for the future, knowing that history has given us a hard time for these countries, and now Egypt, unless they solve their problem with the Ethiopians for the 55 billion cubic meters and 18.5 billion cubic meters for Iraq and Egypt, and Sudan too. Sudan 18.5, sorry, not Iraq, Sudan 18.5, and 55 for Egypt. Can anybody give me a hint?
I'll take a shot at that. A very good question. You're talking about transboundary water, basically, a big issue in the region. I believe the answer is in looking at water management as a global issue rather than looking at it at a local scale as a national issue. We have a project now with MIT where we're looking at developing what we call win-win situations. Sometimes the water or any resource, if you manage it globally, you can maximize the output from it for everyone, rather than attributing basically that resource partially to different groups and each one manages its part. Let's go back to Egypt, for instance. Look, the Renaissance Dam is going to be mainly, supposedly, for hydropower production. So it's going to take time to fill it, but eventually afterwards the water is still going to be going through the Nile, we hope. The point here is when we did the case of the Nile, what we realized is that you can actually produce more food by irrigating in some parts of Sudan than if you transfer the water to Egypt. So if we do the work and evaluate how much we're going to be producing by doing the irrigation and the food production in Sudan, where we have land that's more fertile, less water gets lost by evaporation because we have less heat, basically, less irradiation. What we can do is produce more than what Egypt would have produced. So Egypt can still get more than its part, in a certain sense, more than it would have produced as benefits if it took that water. And Sudan is still going to get something and is going to basically create jobs for the population. If you optimize a system globally, any problem, if you optimize it globally, the optimum you're going to reach is more optimum than the sum of the optima that you obtain by optimizing locally each subgroup. So we have to start thinking about water as a global commodity, and we need to work together. That should lead to additional benefits for everyone. I don't know if it makes sense what I'm saying.
How can you convince Syrians to close all the farms that started recently in southern Syria? Inshallah, إنه الحرب بيخلص.
Inshallah.
But they have taken from us, Jordan, the Yarmouk water. And they started and have beautiful farms in southern Syria. How can I convince them to give me not all my water share back, half of it? I was supposed to get 730 million cubic meters. I am getting about 100 now.
It beats me.
You cannot.
Now, I don't have an answer to that question. Sorry.
Is there, yes, there's a question back there.
Thank you very much for all the speakers. My name is Ali Al-Amoudi, Dr. Ali. I'm a senior, a former United Nations Development Program advisor. My concern is the sustainability, and to Ms. Alia Abdurrahman. I really appreciate it. And your colleague about the focusing on this generation, the new generation, sustainable development is the meaning of what we have to conserve our resources, natural resources, to the next generation. So here we can see in front of us a model, a real practical and experimental reflection of the philosophy of sustainability to this school and to the new generation. I think this Lewis school is the only unique in the GCC country to be recognized as a sustainable school. Now, Alia, as you mentioned, and you showed the reduction of the carbon footprint by means that the reduction of the consumption of our fossil fuel carbon by using the solar energy, you say, and also by recycling, and also the mode of water recycling. But you didn't mention anything about the waste, the recycling of waste, other than the segregation. This is also a good trend in the school. If you try to use the garbage, the waste that you have, and try to segregate it, teach the students there or your colleagues how they can segregate it and how can they get use of it in one way or another. The other thing is also to encourage the organic farming, organic agriculture. So in the school itself, for these are also, you will complete a full picture of sustainability or the school sustainability. Thank you.
Thank you for your suggestion, and I'll make sure to tell my...
Actually, back in our school, we did have waste segregation. We were, like at the end of the school, the garbage that is in the playground, we actually did segregate it. And you talked about organic, yeah, back in the KG junior buildings, we actually do encourage kids to plant potatoes, tomatoes, and such things. So we actually did take that into consideration.
Okay, besides the experimental or the project that you have, do you teach it in your curriculum?
We do, yeah. Yeah, of course. Yeah. There's also awareness all across the school, like what we do. We give presentations in classes, yeah, so it is in the curriculum.
This is a good thing that we need to know, thank you, because now UAE is trending. For those who are, who are not living here in UAE, we are having the 2030, our vision, the strategic vision, or what they call it, the green strategy for Abu Dhabi. And we have 2021 vision for the whole UAE. So that's the trend where we have to go green, where to minimize our footprint, and also to have a generation like you, the next generation, to hold the sustainability concept and to reflect it in all these projects and things. Anyhow, thank you very much for them.
Totally agree.
We have some questions up here.
Thank you very much. I don't have a question. I have just a comment. Today, I'm really very happy to hear that there are schools that are adapting, these new technologies and to conserve water and recycled water. I think, in my opinion, this experience should be widespread, especially here in UAE, because this is the best, I think, campaign of awareness campaign rather than just sending, let's say, literatures or here and there. And seeing is believing. And now when students see things like that in their own school, I think this is a very interesting experience for them, and they can take it in their life for other things. So my comment is, my recommendation here is to whoever sponsoring this, is to increase this and widespread it in more schools. Thank you.
I think today we hear two good examples about how the young researchers that work in the research. And we heard, I think, or was two important, it were two important topics, one of which is climate change by Andrew. You had, I think, excellent presentation. And the second one by Alia, which is about the consumption of the water. But let me ask maybe Andrew and other experts in this field of the water education. Do you think that the theme that you selected, especially the climate change, is appropriate for the young researcher to start, or a little bit advanced? Maybe Andrew can comment, maybe later on we need to listen from the, maybe Kari, you can comment on that. You want to go first?
Sure, sure. So the question was if climate change was maybe too advanced for some of the younger generations. I just want to make sure. Well, I think that when I went into research with Professor Shalene Jain, who's in the audience right now, everything was very foreign to me, and that's why I think that with the STEM Academy model of having several years of research, you not only do the research, but you spend about a year understanding what everything means. So by the end of at least 1 year, nothing seems so foreign, and you can actually start doing new research and stuff that hasn't been done before. And that's what I found with my experience. Maybe Mr. James can comment more on that.
I actually think that you could start younger. I think the level that Andrew operates at is obviously drastically different than a fourth grader would do. But I think the topics are so critical that you have to start the initiation of at least the thought process early on. So in a case like Andrew's, I mean, he could go and disseminate some of that information to younger kids and get them interested at a different level. But I think the key is getting kids involved earlier. That's really what I think. And if you apply that to our stormwater model, that I didn't get a whole lot of chance to talk about, it was running short on time, but that model is, actually Andy's involved on that. Andy does everything. But he's involved there. Those kids today, as we speak, are at the Children's Water Festival talking about the work that they're doing, that they learned about wireless sensor networks, and going and talking to, in our country, it's grade 4 to grade 6, which is about 9 to 12-year-olds. So they're there right now presenting that information. So I think a key is getting to the younger kids, I really do. It's important. And the water cycling that we saw, this terrific project that they had, I think that's a classic example of how that could be implemented, at kind of any age group. I think it's important. The youth is the key.
Okay, I know we're well past time, so we'll call the session to an end, but if you have further questions for the panelists, they're here, and I'm sure they would be very happy to talk with you privately. Thank you very much.